Parameterized curves. This is our topic for today. And well, if we only speak of the calculus courses, we study parameterized curves in Calculus 1, Calculus 2, and Calculus 3. So I would say this is an important topic that we will start discussing, and then we will continue throughout future semesters. Okay, so what is a parameterized curve? Well, first of all, let me just speak about in R2, and then I will also talk about R3. A parameterized curve in R2 is a function of this form, okay? X of t, comma, y of t. This is, you see, a tuple. This is in R2. And the independent variable, t, is called the parameter. And these functions independently, just x of t or just y of t, are called the component functions. Okay? Now, quite often, maybe I will put this in some stars, often this parameter t is time, and this x of t, comma, y of t gives the position on the plane where we're talking about motion in space. Okay, so you have x of t, y of t, and you have some point, this particle, and is moving on a plane. Okay, and this differs. We have discussed, even day one of Calculus 1, we discussed motion on a line. Okay, but now, because we have these two components, we can think about these parameterized curves as being motion along a plane. Now, the other thing that I will mention is there's no reason to restrict to R2 here. You can have a parameterized curve, x of t, y of t, z of t. This would be in R3. And here, well, the component functions are three of them, x of t, y of t, and z of t. And this would give motion in space. Maybe I'll write gives motion in space. Okay. So I guess in theory you could have 4 components, 5 components, and have motion in a 5-dimensional space, but primarily we will be working with R2 and R3, okay? Here is an example. We have this parameterized curve. We have t plus 1, t squared minus 3, and I didn't explicitly mention here that t is time or that t must be bigger than or equal to 0. So let's just plot a few points and sketch, and I will use some negative values of t in this example. So we have t, we have the x component, and we have the y component. And let's try minus 2, minus 1, 0, 1, 2, 3. We'll plot these 6 points. At minus 2, we have negative 1 and 1. At minus 1, 0, and negative 2. At 0, we get 1, negative 3. 1, we get 2, negative 2. When t equals 2, we have 3, 1, and finally when t equals 3, we have 4, 6, okay? Let's sketch these points, okay? So we see minus 1, 1, and then 0, minus 2, 1, minus 3, 2, minus 2, 3, 1, and then 4, 6. And this parameterized curve, didn't quite go through this point. Okay, it goes like this. And typically we will put arrows like this to show the direction as t increases. Okay, so this is a sketch just by plotting these 6 points. What we see here, just graphically, this looks like a parabola. And how could we see that? Y is some function of x. Well, sometimes you can eliminate the t to get y as a function of x. So let's eliminate this parameter t. Okay, how would we do this? Well, we know x is t plus 1, and this means that t is x minus 1. Okay, just solving for t here. And then if y is t squared minus 3, this would be x minus 1 squared minus 3. And here you see, I could even multiply all this out. This is x squared minus 2x plus 1 minus 3. We get, finally, x squared minus 2x minus 2. And so the path traveled is on this curve. And we see this sketched, okay? And we will, if t ranges between minus infinity and infinity, we will fill out this whole curve. We would, for more negative values of t, we would have this part up here. You see, because if t ranges between minus infinity to infinity, then so does x. And we would fill out the entire curve. Y is x squared minus 2x minus 2. This example is still on the board because I will work with it. But first I want to talk about something that's quite important. If you are given position, so here x of t, y of t, this could be a point, the location on a plane, or here with 3 components, this would be your location in space. Okay, this is position. Well, the velocity, let's think. If we think back to motion along a line, to get the velocity, we just differentiate. Okay, well, this is a tuple, right? It's what's called a vector. And how are we going to find velocity here? Well, the beautiful thing when you have, another way to say this is a vector valued function, we just differentiate each component. So the velocity will be x prime of t, y prime of t in this case. And over here, it would be x prime of t, y prime of t, and z prime of t. Okay? And then another thing I will say, acceleration. What's the acceleration when you have motion along a line? It's the second derivative, or it's the first derivative of velocity. And it's the same idea here, except it's component-wise. So this would be x double prime of t, comma y double prime of t. This vector, this gives us acceleration. And if we are in 3 dimension, it would be like this, and like this. We just differentiate each component. Okay, now let us return to our example that is still on the board. Our position was t plus 1, t squared minus 3. And so the velocity is, differentiate, it's 1, 2t. And the acceleration is, differentiate, it's 0, 2. Now let's just think about, let's see, this acceleration is constant. The way we typically depict a vector, which these are, so I will graph a of t, here is you draw it, let me get a different color, as an arrow, and this is 0x and 2y. So you start at the origin and the arrow ends at that point. So here is a of t. Okay, it's constant. Now the velocity is not, so let me draw a few of these. I'll do it over here. When t equals 0, the velocity is here. This is v of 0. When t equals 1, the velocity is 1, 2. When t equals 2, the velocity is 1, 4. And finally, the last one I'll graph is maybe when t equals 3, the velocity is 1, 6. Okay. But you see here, velocity is a vector. And what is a vector? Well, you will have a lot of time to think about this in future calculus classes, but a vector, it's an arrow, and a vector has a length and it has a direction. And this is what makes a vector, whereas a number, well, there's no direction really to a number, okay? So a vector has both length and direction, and velocity is a vector. If we go back thinking about the first few days of class, we discussed motion along a line. We discussed velocity, acceleration, but there was also another concept, which was that of speed, okay? And back then I was talking about just running on a straight line or driving my car on a straight line. I don't remember which one, but I would either go forward or backward. And velocity then, it had the direction. It was either had a plus or a minus. And speed, there's no direction, right? It was just a number. It was like 75 miles per hour, something like this. So the question is, what would speed be in this situation? You see, because speed is not a vector. Speed is a number or a scalar. There will be no direction in speed. Speed is, this is the length, sometimes called magnitude. This is another word, of the velocity vector, okay? So you see here I have graphed 4 of them for this particular position function, but you see they all have different lengths. Well, they all have different directions too, but speed is the length, and length is a non-negative number. What would this length be? If this is some point a comma b, so the length of this, and when we write this in the calculuses, it can either mean the point AB, or it can mean the vector starting at the origin and ending at that point. You will see this throughout calculus 1, 2, and 3, okay? But the length of this vector, well, this is A, this height is B. If you think Pythagorean theorem, this hypotenuse, the length would be square root A squared plus B squared. Okay, so immediately we get that the speed is, it's the square root of x prime of t squared plus y prime of t squared. Okay, this is in R2, and in R3 you just have one more component. This would be the speed of a particle. Okay, so it's just the length of the velocity vector. We take the derivative of position and then we take the length. Now, we'll continue with this example a little more. The speed here, at least as a function of time, is the square root of, we take 1 plus 2t squared, which is square root 1 plus 4t squared. This is the speed as a function of time, and for instance, the speed at t equals 2. Well, I have speed as a function of time, I just evaluate at 2. This would be square root, this would be, 17, okay? Here's another example. You notice we are still in R2. We will do some examples in R3 today also, but here we go. This is in R2. First, eliminate the t to find an equation involving x and y, find the velocity, and find the speed at t equals 0. Okay? Well, we know that x is square root t plus 1, okay, here. And so that says that t plus 1 is x squared. Well, I'll just leave it like this. I could solve for t, but you notice I have a 1 over t plus 1 in my second component. And so the final answer for A would be y is 1 over x squared. Now, this is very different than the first example we did, because if you look at this, maybe I'll put this in pink. Here, what do we see? We see that P of t is only defined for t, let's see, we need strictly bigger than minus 1. Okay, this part we need bigger than or equal to minus 1, and here not equal to minus 1. So it's only defined for t bigger than minus 1. And so what this means is we do not see the entire curve y is 1 over x squared. Because in particular, x can only be positive. Okay, so we're not going to fill out this entire curve, only the part where x is positive. Okay, and that's different than before. Now, that's a nice observation. Let's move on and work with part B, velocity. Well, we just differentiate each component. So this would be 1 over 2 square root t plus 1. And then this is going to be minus 1 over t plus 1 squared. Okay, we differentiate this component here, differentiate this component here. This is velocity. Okay, that's all there was to B. And now C, we want the speed at t equals 0. Well, the first thing we want to do, at least I think it's easier, to find the velocity at 0. And that will just be, we'll have numbers here, and then we take its length. The velocity at 0 is a half, comma, -1. And then the speed, which is, I will introduce this notation. This notation here, it looks like absolute value signs. This is notation for the length. This is a notation, or a magnitude. Okay, that's just a comment. Well, here we go. The speed, which is the length of v of 0, this would be the square root of a half squared plus -1 squared. This is the square root of 5/4, which is here. So this is the speed at time t equals 0. Here is an example in 3 dimensions. I haven't written it in its vector form. I just listed the 3 component functions, but we certainly could. If we wanted to, we write p of t as cosine 3t, comma, sine 3t, comma, 4t. Okay, we want to find the speed at t equals pi, although I will also make some wonderful comments about this example. Okay, here we go. First, we find the velocity as a function of time. When we differentiate these, technically, chain rule, my inside function is 3t. So we have derivative of the outside evaluated at the inside times derivative of the inside function, and similarly here. And then the derivative of 4t, that's just 4. Now let's go ahead and evaluate this at pi. The velocity at pi is, well, we have minus 3 sine of 3 pi, comma, 3 cosine of 3 pi, and 4. Okay, maybe I will think about this over here. 3 pi is here, right? If I put my unit circle like this, here the cosine is -1 and the sine is 0. So my velocity at pi is 0, comma, minus 3, 4. Okay. This is the velocity at pi. To get the speed at pi, we take its length. Square root. It will be 0 squared plus minus 3 squared plus, maybe I'll just put 0. 0 squared is 0. And then plus 4 squared. This is square root 25, which is 5. Okay? So we have the answer here. I finished the problem as it is stated. Okay, maybe I'll put a line. So this was the answer. This is the speed at t equals pi. Okay, but let's generally find the speed. Well, the speed at, say, time t, this is the square root. Okay, we look at each component squared. So we will have 9 sine squared of 3t plus 9 cosine squared of 3t plus 16. Now, these two, let me factor out a 9 from the first 2 terms. Sine squared 3t plus cosine squared 3t. What do we see here? Sine squared plus cosine squared is 1, okay? Even with a 3t, it's fine. Any angle, theta, sine squared theta plus cosine squared theta is 1. And so this is This is 5. This particle, whose position is given by cosine 3t, sine 3t, comma 4t, it's not the case that the velocity is constant. The velocity is not. You see, this is not constant, function of time. But the speed is constant. So it's traveling at a constant speed. So the length or magnitude of velocity is constant. It's just changing direction as the particle moves. Now this is such a beautiful example. Let's look at a maple plot where we can see this curve being traced out in time. I'll do one more example in R3, and then we will move into talking about slope and calculating dy, dx. Okay, this one is fairly straightforward. It's really an exercise in differentiating. We're given position. We want to find velocity and acceleration. Just looking at the three components, we see that t must be positive here because we see a ln(t). Okay, velocity. We differentiate each component. Derivative of 2 to the t is ln2, 2 to the t. The second component, this is product rule. It's first times derivative of the second plus second times derivative of the first. And then this is 16t minus 1. Let me write it this way. ln2 times 2 to the t. This is ln(t) plus 1. And then acceleration, well, we differentiate each component. This would be an ln2 squared times 2 to the t, 1 over t, and 16. Okay? This is calculus, which means we are always interested in the slope. And I will just write it dy dx, slope of the tangent line, or the instantaneous rate of change of y with respect to x. Well, how can we figure this out when you have a parameterized curve? Okay, well, let's just look at our first example. We had p of t plus 1, t squared minus 3. And if we want to find dy dx when x equals 1. For example, okay, you see this one, I don't need anything fancy. In fact, I don't even need to think about it as a parameterized curve, because what did we do? We eliminated the t and found that y was x squared minus 2x minus 2. And so we may calculate dy dx directly. This is 2x minus 2. And at x equals 1, we get 0. Well, maybe let's go and do another one too. So let's do another where we eliminated. We had p of t was square root t plus 1, 1 over t plus 1. And let's suppose we want to find dy dx when x equals 4. Okay? And similarly, just like the last one, we eliminated the t and found y is 1 over x squared, which if we want to differentiate, it's x to the minus 2 dy dx is minus 2 x to the minus 3, which I could certainly write like this. And then at x equals 4, we get negative 2 over, let's see, 64, which is minus 1 over 32. Okay? I've just rewritten what we just calculated by eliminating the t. We found in this first example, dy dx evaluated at x equals 1 is 0. And in the second example, dy dx evaluated at x equals 4, negative 1 over 32. But I would like to find a way to calculate dy dx, it's here, without eliminating the t, because quite often this is challenging, okay, or not possible. Well, dy dx, if I write it like this, well, here I'm really thinking y as a function of x, but what would happen if I multiply like this? Certainly x is a function of t. This product, dy dx times dx dt, we know this is dy dt. This is the chain rule. This was our way of writing the chain rule in terms of this dx or ddt notation, okay? Now, if we just solve for dy dx, we get dy dx equals dy dt divided by dx dt. And this here, I'll put it in a blue box. This is how we will calculate dy dx, okay? Because we have y as a function of t, x as a function of t, we can differentiate each one, and then we just take this quotient. Okay, so let's practice this on these two examples, and then we will do a few where I do not eliminate the t. So in this first example, p of t is t plus 1, comma, t squared minus 3. dy dt is 2t. dx dt is 1. Now, I want this is an important part, at x equals 1. Well, when x equals 1, that's the first component. T is 0. Okay, so I need to evaluate both of these at t equals 0. Okay, so then dy dx at, I'll write it as x equals 1, would be, I'll write it even this way, dy dt when t is 0 over dx dt when t is 0. And this is just 0 over 1, which is 0. So this matches exactly what we found, but you notice I did not eliminate the t here. Okay. Let's move on to the second one. Here, maybe I will just do this initially when x equals 4. We put 4 here. So 4, maybe I will solve. This is the square root t plus 1. We square both sides. We get 16 is t plus 1, we get that t is 15, okay? So whatever I get, I will be evaluating at t equals 15. dy dt evaluated at t equals 15 is, well, we have this, evaluated at t equals 15, we get negative 1 over 16 squared. dx dt evaluated at t equals 15 is like this, which is 1 over the square root of 16 is 4 times 2, we get 8. So now I have a little room left over here. dy dx at x equals 4. Well, we just take this divided by this. So it's negative 1 over 16 squared times 8. Right? We invert multiply. And what do we get here? Well, we have a 16. Ah, very nice. It's exactly what we calculated before, okay? Negative 1 over 32. Yet again, you notice I did not eliminate the t. Let's look at this example. We have p of t, this is in R2. It's t cubed plus 2, comma, t to the 4th plus 17. This hat you will often see on top of a vector. It's just notation. Okay, we want to find dy dx at this point q, which is 3, comma, 18. Just by inspection, you see, we see that t equals 1, right? Because we need t cubed and t to the 4th to both be 1. This says t equals 1. Okay, so we want dy dx at the point q, which is dy dt over dx dt, and maybe I'll write it this way, all at the point q. Well, dy dt is 3t squared, and maybe here I'll do it this way, at t equals 1. In the denominator, we have 4t cubed at t equals 1. And you see here, this is just 3 over 4, okay? So the instantaneous rate of change of y with respect to x at this point is 3/4. Here is my last example. Here we want to find both dy dx and dz dx. For this curve, square root t, cosine t, sine t, and we're given the point is square root pi minus 1, 0. And just looking at this, the first component is square root t, and we see the value is square root pi, and so it must be the case that t equals pi here, okay? So let's do the first one, dy dx, evaluated at, maybe I will write the point, okay? This equals dy dt at t equals pi divided by dx dt at t equals pi. dy dt is negative sine t, and dx dt is 1 over 2 square root t, and this would be evaluated at t equals pi, evaluated at t equals pi. Well, the sine of pi is 0, and then the denominator is not equal to 0, but we have 0 over a number, we get 0, okay? dy dx is 0 here. And then finally, dz dx, again, at this point, square root pi minus 1, 0. This is dz dt at the point, or at the value t equals pi, divided by dx dt at t equals pi. Here, well, first of all, derivative of sine, cosine. Maybe I'll go ahead and evaluate it. We get cosine pi, divided by, and this would be 1 over 2 square root pi. Cosine pi is negative 1, and then in the denominator we will invert multiply. We get negative 2 square root pi. So this is the answer for dz dx at this particular point.